So we partner with Zed Oil. They're a company based in Southampton, PA, and they manufacture wax products for prototyping. They were founded by Anthony and Rachel Prito, and they use a lot of plastics and recycled materials in their mixes. And they recently acquired a vat for mixing because casting is one of their processes. And a vat of comparable size with the same features would cost thousands more. So what we are doing is saving a ton of money. And also, the vat they have now, the process for making the wax is very tedious and labor intensive, so we are trying to streamline that process. This is the current CAD model of the vat. And the project scope. We are going to install a motor on top with an auger that will mix the fluid. We are adding heating elements to more evenly disperse the heat, and we are also creating a user-friendly system to control all the heat and the motor. And our requirements are simply to mount we are going to mount the motor and the gearbox to the top. We are going to use a VFD to control the speed of the motor. We are going to add an e-stop, and we had to choose the height and the blade length that would best fit the fluid. And the heating elements we're planning to add 2 extra 540-watt strips of heat tape on the bottom conical section of the vat. And we're also adding a 400-watt piece of heat tape to the outlet pipe so it doesn't solidify as the vat is draining.
So for our ethical and safety requirements, obviously we need to keep the employees that are using the vat safe, the company safe, and just like the environment safe, because they are obviously melting wax. Specifically for mechanical, we had to add an e-stop to make sure that if something were to happen, they were able to stop the motor, so nothing else got damaged or none of that. So here is a CAD model of our modifications. So we plan on moving the hinge up 9 inches towards the front of the vat. So we could mount the auger in the dead center of the vat. We also wanted to mount the motor parallel to the hinge, so when we went to go and support it from underneath, we were able to support it all the way across the bottom of the lid.
So the first thing we had to figure out was what type of impeller we wanted to use to mix the wax. And we decided to go with a high vein dispersion blade for a few reasons. It's very good at mixing moderate to highly viscous fluids and really increasing the radial flow that you get off of them, but simultaneously not introducing too much shear friction, because at the moment they're having a problem with one of their smaller vats where if they leave the motor on for too long, it overheats the wax and ruins batches at a time. So to determine the blade size, the general rule of thumb is you want it to be about a third of the diameter of the entire cylinder that it's mounted in. So we chose 16 inches for ours, and the 16 inches is valuable because it lets us calculate the tip speed, the speed at which the actual ends of the dispersion blade are going to be rotating. And we knew that to get to get good dispersion, we wanted it to be somewhere around between 500 and 1200 for good dispersion without introducing too much friction. And that is going to be bolted to the shaft just on the bottom. And now for the shaft length, you want to mount your blade about its diameter from the bottom. So ours is a cone, and it also loses a little, or adds some length because it has to reach out of the vat to get into the gearbox. So ours is going to be about 28 inches long, which should leave it about 16 to 17 inches above the outflow pipe, and about an inch in diameter, so that it does. So for our motor and gearbox, we're going to be using an AC induction motor that can generate 2 horsepower and spin about 1,800 RPMs. We really needed to up the torque on that, so we attached a 10-to-1 gear reduction box. The motor itself and the gearbox could produce somewhere around 80 newtons per meter of force, but there's a mechanical limit on the gearbox, so we're only able to calculate out to produce about 628, which is going to be about 72, which should still be more than enough for our wax at that viscosity. It's when we try to mix it, we're going to need to generate somewhere around 58 newtons per meter, or newton meters, to spin the blade at about 180 RPMs. So we're going to control the speed with the VFD. That will give Anthony the ability to start and stop the blade, and also to control the speed at which it rotates. With the 3-phase input, it's good up to 2 horsepower, so it should suit our motor quite well. One other thing we had to add was a peristaltic pump. Currently, they add dye towards the end of their manufacturing process by climbing up onto a ladder with respirators, opening the bag and dumping in 1.5 quarts of dye, and they would really like to do away with that, so we are going to mount this peristaltic pump on the other side of where the motor and gearbox are currently mounted. And so when they crank that up all the way to, I think it's 34 RPMs, they're going to be able to go up to 30 milliliters per minute, and that should take about 45 minutes to fully introduce the dye. We had to use Viton tubing because they also add acetone to their dye. So if we use something like silicone, eventually it would have started to eat away at the tubing. The good thing about this motor is it's also independently powered and controlled, so this is not going to be a part of like the larger circuit that we would do. So for the heat tape and the PID, currently on the back there's 4 pieces of 720 watt heat tape on the sides and 2 pieces of 1008 watt on the bottom. So as Jackson said earlier, we're going to be adding 2 pieces of 540 just on the sides, and then a 400 watt piece to wrap around the outflow pipe, because they are also having a problem now with the wax cooling off while it's in that pipe, solidifying, and it's a big mess to try to do. So the solid state relay is going to serve as the intermediary between the heat tape wired parallel with each other and the actual PID. It's just going to shut off the heat tape when it starts to get too hot, and the PID will get that information from a thermocouple that's already attached to the vat and will be plugged into the PID. So we're going to have 240 volts coming in for our motor, and 120 for our heating elements. The problem at the moment is all of those heating pads draw a lot of power. I think or a lot of current. It's somewhere around 54 or 55 right now. So our solid state relay is rated up to 60 amps, but that is also very expensive. I think we would like to use that money elsewhere if possible.
This is our WES subdivided into mechanical and electrical components, as well as the testing phase and the management phase.
So this is our schedule for the first semester. It was basically come up with the projects, get a basic design, and now we're currently standing. So here's the Gantt chart for our semester 1. And this is the vague schedule for semester 2. So we plan on ordering materials between now and the beginning of next semester, so they come in on time. Preparing the tank for modifications, building the design, and testing and refining. And here's the Gantt chart for semester 2. this is our electrical budget. Overall, we ended up spending $641.43. And for our mechanical budget, we spent $1,325.10. Overall, our budget is $1670.03 for our final. So the modifications that we may not make, but maybe other groups later in the future, adding a vacuum pump. So currently, when they need to add extra racks into the vat, they have to get up on a ladder and dump like buckets of plastic into the vat. So we wanted to come up with a vacuum system where they take basically a hose that runs from the bucket back into the tank, so they don't have to climb up on a ladder. We also wanted to add more thermocouples for a comprehensive temperature reading.
Our testing plan, we are going to build and design as planned with the things we have set out, and then we are planning to test each component individually to make sure it works before running a batch. And then the batches will be run with or without us on the site, considering it is about 2 hours drive from here, and we do flexes and other things during the day. And then, of course, afterwards, we need to check for inconsistencies in wax to make sure it does what it needs to do. In conclusion, our scope needed to be narrowed down from the beginning. We had a lot of little ideas that we wanted to implement in there, but we figured out what would be best to concentrate our time, money, and effort towards the main functions of the vat so we can get up and running. Just our references, code of ethics, the Indico website for how to calculate tip speed, and the OSHA regulations that have the e-stop definition. And we'd like to thank Dr. Gamari for being our advisor. We appreciate you. And Dr. Benarts for running all the senior project stuff cleanly. And we'd like to thank Anthony and Rachel Prado for sponsoring us, putting their faith in us, and our fellow classmates for moral support and a shoulder to cry on. Questions?
What's the range of speeds that you have to vary the motor?
So it depends a little bit, but anywhere between, so 180 RPM is the max, but once it's above 130, 140, it should be.
You're not going below 130?
I mean, they could, but so the dispersion is what we're really going for. And it's once you get it to a certain speed, it pulls particles in from the top and sort of flushes them out the sides. And that really only starts to happen for these like moderately viscous fluids.
The reason for my question is you said that this is an induction motor that you're using, an AC induction motor. And I'm not, you need to be sure that that motor is spec'd for the lower frequencies than 50 hertz. Most induction motors are spec'd for something like 50 to 60 hertz.
Yeah.
And you better be sure that that motor is suitable for those lower speeds.
They have gears. They have gears.
Yeah, but it's an induction motor.
Okay. So, first of all, you guys are dealing with a three-phase AC power. Safety first. Okay. 100%. Like, don't take unnecessary risks, because that's okay. Anything you're not sure about, get more information. Don't take unnecessary risks. Okay. Especially safety. Second is, I really wish you guys for a project like this one, very practical. You should actually always include the electrical circuit diagram as well as for this one, you need a control cabinet. You need a control cabinet. You didn't show any of the design.
Yeah.
Understand what I'm saying? You need a control cabinet that says what's in there, what are the layout, where is the motor, where is the power, where is the control, blah, blah. I'm not even sure, but you mentioned electric control. How would you, what kind of control are you using to control it? What are you controlling? Because without those diagrams, I really don't know the details. So,
Yeah, so yeah, we wanted to include like a control box and stuff, but they we haven't been able to get a good enough.
So you're just adding stuff to their control box?
Uh,
That's the right risk. I don't think the owner would feel comfortable to do that because you mess up their existing system. Usually the owner, they don't necessarily want you to do that. You understand what I'm saying? But maybe, but because that's always a risk. You start making it better, you could also make it worse. So that's always a bad. Unless Anthony is really confident in you guys, but again, we all can make mistakes. But you see that point, right? So I don't think that you are adding something to existing system because you could jeopardize the existing system. I think it's very possible you're designing new control packet and stuff like so you need to look into that. Because you have the VFP stuff, but it has to sit somewhere, has to be full cost somewhere.
Yeah, it's all specs to fit on pin rails. We just haven't figured out exactly how large.
So are you proposing to control using PLC to control this? Is that the plan?
So, no. So originally we were going to, but with the time limit in our budget, we figured we would scrap that idea for right now and use so currently they're running their motor on a timer, like a 15 minutes on, 15 minutes off type deal to control the shear friction. So we talked to Anthony and he was okay with using the timer for a little bit longer, and then controlling the heat tape with the PID.
But what controller are you using to control the temperature?
It gets set at the PID currently, and then it has each set of
PID is an algorithm. What hardware do you use to control that?
It is it's pads of heat tape that go through a switch into the PID.
No, I was trying to explain to the PID is an algorithm that sits inside the computer. What computer do you use to control it? What do you, a microprocessor, microcontroller, or you need some sort of a computer to do the job, right? To process it.
Yeah, so it's just like a general display that has.
That's okay. We need to have a conversation later. Right? But you see my point, right? Because that algorithm has to sit somewhere, has to reside in somewhere. Unless you are doing a hardware, are you doing a hardware?
It's a hardware PID.
You're doing hardware?
Yes.
So you're designing a circuit board for the controller? Because nowadays people don't do that anymore. I hope you understand what I'm talking about. Because you can use a hardware PID, but that's much more effort. That's why people move to computer digital stuff, because you are talking about something 50 years ago. I'm not sure if you understand that.
In terms of temperature, what range of temperature do you need to reach in order to get the best configurations to be able to basically
So yeah, our calculations and our viscosity are all taken at around 270 degrees, which is pretty much the temperature they want their fat to sit at.
And how are you going to provide that temperature to the system?
It's currently controlled through heat tape that is connected to a PID or source console.
There's also, if you're able to get a temperature reading in the vat, although it might, considering its location, it might not be accurate and good at describing the temperature of everywhere.
And in terms of maintenance, after you finish one batch, what do you need to take into consideration to reuse that system again?
So one of the things that needs to happen after a batch is made is there's some residue that cools down on the surface of the vat, and what they do is they just take Anthony has been taking a large spatula to sort of break up the chips of solid wax, and then hold in for future batches and add them in later. So that's one of the things. But one of the problems from not having the outlet pipe heated is that there would be literally a solid tube of wax, and so that's one of the things we're solving, so that doesn't have to happen, or that doesn't cause a problem.
Okay, I understood now. So you are using a commercial hardware-based jetting controller.
Yes.
That's what I was looking for.
Okay.
Because that's a commercially available hardware-based jetting controller.
Yes.
Yeah, that is what they already have running.
Okay, that's otherwise because that's you see that's there are two, and we learned that, right? One is digital weight, one is analog weight. So this is analog weight